Joseph, comes to us from University of Hyderabad and uses the invertebrate grasshopper to understand sensitive.
Can you hear me? Yeah, okay. So I work with this little animal, grasshopper. Okay. And I try to use tools like electrophysiology, imaging, behavior to understand functions of network of neurons with a small organ. So I'll try to divide this talk into two parts. First of which is what I did towards the end of my postdoc with Mark Stopper, and later part I'll try to show little excitement we have in our current lab. Okay, so this is the work I did with Mark's lab, studies done, and this is the grasshopper which I was working with in the previous lab, Americana. And if you open up the head of the grasshopper, and this is the kind of experimental setup in which we do the recording. So this yellow stuff in the middle is the brain of the grasshopper. So we can stick in electrodes, we can apply stimulus, and do all kinds of manipulation with this system. So it's a very nice system to work with to understand, as we said, the network level. So predominantly our lab they used to work on olfactory pathway. So in insects the olfactory system has its input in its antenna here, which has a receptor neurons. So you can record from the various stages in the olfactory pathway of the insect. Almost at any level, if you do almost any arbitrary volatile, some kind of response. Okay, so that's for comparison. This is a human brain, and that's the grasshopper's brain, and it's just showing the synaptic densities in the grasshopper brain. So it is more modular in some sense compared to the human brain. So we can target stuff a little more better. So we can do a variety of measurements from this brain. For example, you can record from a single cell and complete membrane potential. You can look at the morphology. You can understand what kind of neurotransmitter it expresses and so on. Doing immunohistochemistry. You can record neurons at the same time using extracellular techniques. So you can monitor the population of neurons, but you can identify, okay, this particular spike came from a particular neuron, this set of spikes in a particular neuron, doing this process called spike sorting. All this works very nicely in the system. You can do calcium imaging, you can do intercellular recording, so we can look at what kinds of stuff matters inside the cell. It's mostly governed by calcium and how does it correspond to the spiking responses in those cells. So it's a very versatile organism in that sense. So coming back to the system, the olfactory system of the grasshopper, I'll give a brief introduction to that. This is the grasshopper and this is the antenna. If you look closely at the antenna, you will get this kind of dot structure, each of which has a very fine hair-like structure called sensilla, which is porous and through which the odorant can go into the medium surrounding these neurons called sensory neurons. So this is a cross section of the sensilla. There are pores through which odorant can go in, and this is the cilia of the sensory neurons. There will be one or more sensory neurons in this particular cilia, sensilla, and each sensory neuron expresses only one type of receptor. So which is denoted by the color coding of the neuron. So basically, if you look at the ensemble of receptor neurons available to you, each of them is expressing one particular receptor type. So this is sort of representing the ensemble of receptor neurons. And any given odorant, which is this molecule represented here, can probably excite a subset of them. Some receptors are very specific to certain types of molecules. Some of them can be responsive to a wide variety of molecules. And usually the ordering event for the insect or any for that matter any of us is not just one pure molecule. It's usually a mixture of molecules which happens to arrive at this antigen. So that's the event which the animal has to detect and sort of understand what stimulus it was. So it's in general an ordering event evokes responses even if it is very little across the population of receptor neurons. So that's a critical thing to be kept in mind. Of course, the environment in which the cilia is present is very complex because the ordinary molecules have to come in, maybe they are hydrophobic, has to go through this medium and bind to the receptors, the local channels, and there are multiple mechanisms by which the transcription takes place as far as we understand now. And in some cases there are these intermediaries called olfactory binding proteins which carry the ordinary from the surface to the receptor. Sometimes the ordinary binding protein is what binds to the receptor. And so it's a very complex transduction machinery which is sitting there and often prone to noise and yet has to be sensitive. So this is I think it's a bit bottleneck in this kind of a scenario. And so these receptor neurons which express the same type of receptors converge onto a structure in the anginal lobe. It's like analogous to the olfactory bulb for mammalian systems. And they converge onto the same center, the glomeruli. So basically one glomeruli receives input from the responses of neurons expressing a particular type of receptor. And there are a large number of glomeruli of the order of hundreds in the insects, of the order of thousands in the mammalian systems often. And there are these local neurons which connect between them. And from the glomeruli, the information go on to the structure called calyx of the muscle body. And these neurons which carry this information, and there is no other path which carries information from anginal lobe to further areas in the brain. And those neurons are called projection neurons. These are analogous to the mitral cells in the mammalian system. And here they synapse onto this large number of cells called kinase cells. So at least in the insect olfactory literature, or in the community, we sort of tend to look on these as analogous to the piriform cortical pyramidal cells in the piriform cortex. So a large number of them. And so the key difference between the synaptic convergence onto this projection neuron versus that of the kinase cell is that projection neurons tend to receive input from neurons which are in some sense identically responding because they are expressing the same receptor type. And kinase cells tend to receive input from large number of receptor type information. So this is like a huge convergence of input from a variety of receptor types. So that's basically the system we are dealing with. So how do these cells recording at all these levels, right from the receptor neurons up to the calyx, and now we do it even beyond the calyx. These are examples of the response. So if you record from the sensory neuron extracellularly, then you see something like this. And this horizontal bar represents when you apply an alternate to the antenna, and it happens that this receptor neuron has the receptors which will bind and respond to this alternate, and then you will get this burst of spikes. So two things to be noted. One is that there is a fairly heavy baseline rate of receptor neurons, and there is an even higher rate of activity when the alternate is appropriate for the receptor. And if you come to the into the anginal lobe itself, you record for the projection neurons. They usually exhibit these multiphasic responses, which are often having inhibitory and excitatory phases. As you can see here, there is an excitatory phase and an inhibitory phase. And even they have a fairly large amount of baseline rate of fire. So here the baseline rate is of the order of 5 spikes per second, and here is of the order of 2 to 3 spikes per second. And these loculations in the locus does not have sodium action potential. So they have these calcium spikes, And so this is convenient for us because when we stick the electrode, the extracellular electrode into the antigen lobe, we are sure we are recording from the projection neuron. All the spikes come from the projection neuron, which is not possible in many other insect systems where they have even the locking neurons have sodium action potential. So that's one key advantage with working with the grasshopper system. And then it projects on to the mushroom body, and if you record from the Kenyan cell, what you see is something very different from these cells. The Kenyan cells are very silent at rest, they hardly evoke any action, have any action potential, and when you give orderance, you usually have a few spikes. And currently the notion is that most of these Kenyan cells are silent, and a few of them generate one or two action potentials or a few action potentials specific to that organ and specific times within the organ response to the organ. I'm not 100% sure of that because the amount of sampling we have done in the mushroom body is not, I think, enough. So at least one thing we are sure, the baseline rate is very flat. And this part of what previously was thought to be the true story is now no more correct. Looks like this inhibitory correction which provides the feed-forward inhibition of the muscle body, there is not sufficient evidence for that. So another feature which you have to observe is that if you record the field potential from the mushroom body calyx, what you see is in response to the ordinal, you get this beta rhythm, so around 20 Hz of synchronized input, subthreshold activity going into the Kenyan cells, so which are generated because of this feedback inhibitory network here, which is driven. So this mechanism is very well understood, and so naturally these cells tend to spike at the particular phases in the subthreshold, and because of which you get these subthreshold oscillations in the membrane potential, and because we are averaging large number of such subthreshold activity in the field potential, you get this beta rhythm. So you can get something like E. This is sort of analogous to the EEG, and you get this beta rhythm in response to the organ. Okay, now in this talk I would like to look at why, for example, is that this kind of decrease in the baseline activity takes place as we progress down the network, right, from sensory neurons, which has around 5 spikes per second of activity, to the projection neuron, which has around 2 spikes per second activity, and when you go to the Kenyan cells, there is hardly any baseline activity. Now, does it make sense? I mean, and what could be the reason for the system to be arranged like this? So you have noticed a convergence. So there are large number of receptor neurons expressing the same receptor type converging onto a particular projection neuron, and then they converge, or many of such guys converge into the calyx. So the way I am trying to arrange this, the thought is that first of all we have to see whether this activity in the projection neuron is caused by the baseline activity in the receptor neuron. So somehow we have to lesion these and see whether we can stop this baseline activity. And then we try to argue from a modeling perspective, sort of detection perspective of the Kenyan cell, whether it makes sense to have an arrangement like this. Yeah, so the methodology by which we do this is first of all to lesion temporarily the baseline activity and even the operant response in the receptor neurons. We use temperature to cool down the receptor neurons so they don't spike anymore. And then we keep recording from different portions of the olfactory pathway and see what happens when you shut down these receptor neurons. Okay. So that's the basic notion. So first of all, we make sure that we can shut down the receptor neurons by cooling. So this is the activity when there is no cooling, and then you cool down and decrease the spike rate. We don't really completely shut down 100%, and then you can recover back the activity. So you can do it in a number of receptor neurons, and we can show that you can decrease the spike rate appreciably in the receptor neurons. So this constant barrage of activity is seen going to the subthreshold of the projection neuron and keeps it at a slightly elevated membrane potential compared to what it would have been otherwise. So that's what is happening. So now if this is happening at the receptor neuron, so we cool and stop this baseline activity and then see what happens to the projection neuron. Can we remove the baseline activity in the projection neuron? And that's what we do here. So we start with a normal situation, and so let's say 2 to 3 spikes per second. Then we cool down the receptor neurons, and then you can see that the response to the projection neuron completely goes away. Not only the response, the baseline activity also stops completely. And then you can recover back to the normal temperature, and the order response as well as the baseline activity comes back. And then what we do is that we want to see whether this activity is generated extraneously or not. So we cover the antenna with order impermeable mixture of Vaseline and mineral oil. And then you can see that the order response, though order is applied, vanishes, but the baseline activity persists. So it is not really something extraneous to the antenna which causes this activity. And then to make sure that it can be completely stopped, we cut off the antenna at the end of the procedure, and we can see the activity completely stopped. And we can do with this with a number of animals and number of neurons, and consistently we can see that this activity is caused by the activity in the receptor neurons. And so what's the consequence on the membrane potential of the projection neurons and local neurons and kidney cells to this kind of a deprivation of the baseline activity? So if we do that by doing intracellular recording from the projection neuron, local neuron and kidney cell, in all of them, consistently what we see is that the membrane potential falls and all the spikes vanishes in the cool state. So this is for the projection neuron. And if you go to the local neuron, we can see that, of course, there are no sodium action potential, but we can see 5 to 10 millivolt of drop when you shut down the receptor neuron baseline activity. The same thing with the Kenyan cell. So you can see the subthreshold reduces, the membrane potential drops by around 5 to 10 millivolt in the cool state, and then recovers back. Order response vanishes. Yeah. So now, so this is what's happening in the system. So can we sort of understand why it might be that it should be so this receptor neuron has to be noisy in some sense, because maybe it's trying to be very sensitive, and so it has to respond to almost a few molecules probably coming onto that. But then we can ask, why is it that we need to spend energy in maintaining this activity at the projection neuron level? We could sort of put the threshold in the projection neuron such a way that it shuts off all the baseline activity and responds only to an alternate response. So you can see there is some amount of convergence going to the PNs, and they receive input from a number of ORs. So probably we could put the threshold here such a way that you can cut down the baseline activity and respond only to the alternate. So what we do is that we look at this entire scheme as a detector system. Detection is that this Kenyan cell is a Kenyan cell which is supposed to respond to a particular alternate. The detection has to be that it will respond all the time when the alternate event takes place, which is a combination of receptor neuron activity in the periphery, and at no other time. And what should be the threshold here, such a way that that happens? So, and if that threshold is applied, would there be a baseline activity in the projection neuron? So that's the reasoning that we have to do. So if you vary the threshold here, under what threshold conditions would the KC do a good detection performance? Right. So if you do that, and how do we measure the detection performance? We basically use a receiver operator characteristics, meaning 0% false alarm, 100% true detection. So that's basically a measure of the distance from the diagonal to ideal would be 1. So the distance to the maximum distance from the diagonal for the ROC would give you a measure of the detection performance with the Kenyan cells. So for each given threshold at the PN, you can do this detection performance measure at the Kenyan cell, and you keep varying the threshold and see how the detection performance changes. So if PN threshold is varied, you get the maximum detection performance around here, which corresponds to 0.7 something with this distance. And if you increase the PN threshold beyond a point, you start suffering in detection, right, at the Kenyan cell level. And if you, this shaded portion is the region in which you have good detection performance or maximum detection performance at the Kenyan cell level. And if you plot the baseline rate in the PN during that window, you can see that none of those times you get projection neurons to have 0 baseline rate. So So in some sense, it's telling that if you need to have the detection optimized, you need to allow projection neuron to have some baseline time. I mean, you should not put the threshold such a way that you cut off the entire baseline time. So if you look at this convergence diagram, it makes sense because as I was mentioning before, you have the ordinate information actually for a particular ordinate event distributed across these receptor neurons. It's not just one receptor type getting activated for any ordinate event. First of all, a given ordinate activates multiple receptor types, and usually an ordinate event is a mixture of ordinates. So in general, it is distributed across receptor types. So basically, an ordinate event is kept in a cage, they lay eggs, they lay eggs, and you can hatch them, and you can basically feed them with grass, which you can do very easily. So this is a system actually anybody can rear. It doesn't require any complicated setup to do that. So I would encourage schools and stuff like that to easily rear this stuff if they need to do some physiology experiments or behavioral experiments. And I'm trying to show that it's very easy to do some fun behavioral experiments also with this system. So it fell out this group of young adventurous guys to try and standardize this system and make sure that it is corresponding to the sister cell community. So Shalini, then Ashwin, Shilpi, and Madhura, these are people who are working in the lab. Shalini is around somewhere here. So we went around recording from these cells to make sure that they are all having all these responses. They are LS which are not spiking, PX which are spiking with multiphasic response. They are synchronized, has beta rhythms in the calyx. The tracks are present by using dextran tracing. All these things we have done. So we have a reasonably standardized system now. So, and there are some projects which are going on in the electrophysiology domain in this system now. But I will be talking about two behavioral experiments which I think is fun discussing. So one of them is, I came to this center, which is the Center for Neural and Cognitive Science. So this cognitive science is something which I don't understand even now. So we keep telling that they are not doing cognitive science. So when I look at what cognitive science people do, they most of the time do experiments which involve expectation violation. So what do? A typical experiment goes on like this. So you have a cross coming in here, okay, person sits here and looks at the cross. And then in this cross location, either X may come or O may come. X will come 80% of the time, O will come 20% of the time. And what you do is that you keep recording EEG from the brain over the skull. And you do this a large number of times so that you get enough SNR by averaging the results. And you get that when you have this surprising thing, which is the O coming up as compared to the X, you get a larger deflection in the ERP, which is the average triggered response from the stimulus application. So this is used in various contexts to understand, especially in terms of time when you enter that perceptual domain of having recognized O and O is different from. So, but I don't think we really understand what really goes on here. What it means to recognize it's something different, and then how does it trigger a perceptual recognition of difference. And in almost any sensory system, so this is a response of raster response for recording from projection neurons. You simply apply stimulus, you repeat stimulus for some time, pulsatile stimulus like this, concentration fluctuation, and you stop the application of the stimulus. You often get in at least a subpopulation of the neurons this kind of rebound. And people have called this a violation of expectation. So animal is expecting in some sense that the stimulus is coming on, and then stop, and then this encodes for that the information that this regular stimulus application has stopped. But this does not really come into this domain where we, with human beings, can ask query in other ways, by response measurements, by pressing on a key or something that they have noticed the change, right? So we cannot ask the Casper whether at this time you noticed the change. It's not easy to query that. So we have to take for granted if you do that. But can we create an experiment where we can know for sure grasshopper is expecting this, and then we create a violation and look at it. So we have tried to, I think, come up with a paradigm in which we know grasshopper is expecting something, and then there is a violation. So what we do is very simple. You have a ramp. Grasshopper does a fashion period. So it starts walking along the ramp, but here there is a gap, and there is a light shining on the grasshopper, so it cannot, or it doesn't notice the gap. So it keeps walking along, and then suddenly it encounters a gap, and of course overshoots, and then there's a correction. So we have painted the grasshopper's leg with two different colors so that you can see. So maybe I can show you the. So that's what grasshopper does. Comes back, and now it's twice once more. Now it's looking around. So it is. So what we are interested in this initial phase when it first comes and. What we do is we are interested in right when it actually hits this edge, So the first overshoot and then withdraw. So idea is that if you can show first of all that it reliably does that, then maybe we can put its head up in while we are doing the recording in the brain and make it work on a treadmill and make it encounter the gap. So that's towards which what we are doing. So first of all, we want to see whether we can detect this expectation of violation in terms of behavior. So that's so far what we have been able to do. So we can track these colors, and then grasshopper walks over with time. We can make out the steps. We can calculate the angle with respect to the normal for this leg, and of course it does this nice zigzag. And lo and behold, and where this intercepts the this edge, you can see it overshoots, and then it does something. So we don't understand. So what we are planning to do now is to look at while it's in a head fixed state and is walking and doing this expectation, what goes on in the brain. So what happens when it gets a feedback? Okay, it has done an error, and then it's altering its. So we know that it's recognized as an error and planning a different move. So that's what we are. One of the work we are trying to do. And this phenomenon called thanatosis. Okay, so I didn't know what thanatosis was 1 year back. So this student comes, says that he's interested in doing thanatosis. And thanatosis is pretending death. Okay, so grasshopper pretends death. So when does it pretend death? If you catch a grasshopper, or if a predator catches grasshopper and somehow it leaves it, and if it falls on the ground, the best strategy apparently, even for us or any organism, is that you will stay still, because most of the predators are sensitive to the movement, and they cannot detect if you are staying still. So they will stay still. So if you catch a grasshopper by the thorax and then just put it on the ground, it will lay still for a few minutes. So now the question is it really unconscious, or is it really looking at something? So this is what Ashwin wanted to know. So what he did was he created a setup in which you can sort of press the grasshopper, release it, stay still like that. And then he wanted to apply a stimulus and see whether there is a response to this stimulus. So what's the response that you would notice? So if you look at that, so there is grasshopper, and it is in thanatotic state, and you can see that its abdomen is having this regular breathing. And now this obstruction would come over his eyes. It's like a looming response to the grasshopper, and then it will hold its breath. So for a brief moment. So this can be repeated, and just play through the video to show you that it's not constrained. It actually can come out of the thanatotic state. So it is not. So it seems to be that it is really pretending death in that sense. So and it is actually observing while it is. So we don't really know how to further proceed with this work. That is thought that's interesting to know. So if you look at characterize that time of suppression of the pulsation, you can see that this is when the stimulus comes on, and this is various times statistics of when the stimulus actually stops and goes back from the field of view. You can see there is a much longer response to the stimulus. We think this is mediated by this LOG neuron. So in this setup we are trying to see whether that abdominal pulsation suppression is mediated by LOG by directly triggering the not LOG, NGN neuron by directly triggering the NGN neuron. So I think I will stop there and get questions.
You mentioned about beta oscillations. So what will be the firing rate of the neurons?
So
because PN neurons they spike at very low rates, the pyramidal neurons.
No, so Kenyan cells do not spike at that fast rate. So the suppressional activity which is going into the Kenyan cell is what is this 20 Hz. And so it's basically the activity of the projection neurons that you are really bothered by. And those projection neurons which are getting synchronized, if they fire, tend to spike on that phase of the, and that's what causes the postsynaptic cells. So all of them, when they fire, they tend to fire at a particular phase in that synchronized activity. It is not that all projection neurons fire only at that rate. There are projection neurons which, even when that synchronization is going on, is completely uncoupled to that.
Is it also possible to patch these cells?
Yeah.
And so I'm just thinking about, you mentioned about the convergence of the receptor neurons. And I was thinking of what I'm working on, which is this correlation transfer. And there what we need is somehow intracellular membrane potentials to somehow estimate the impact of convergence. So I'm wondering in this system whether it's possible to patch the neurons and get the estimate of the membrane potential distribution.
Yeah, so we saw some intracellular recording, so we do it regularly. And so if you need to do a simultaneously a cellular recording and intracellular, that's also possible to do that.
Thank you. In the projections from the olfactory lamella, which are quite specific, then to the mushroom bodies, it seems that it's a labeled line and selected neurons. I seem to remember that Gilles Laurent in the locust has claimed that it is not, that they are less specific and that you have an interaction between the glomeruli input with already on the molluscan, on the mushroom level.
Yeah, so I think it is labeled line as much as one receptor neuron expresses one receptor type, and all those neurons which expresses the same receptor type converge on the globuli, and I think is unambiguously labeled line. But I don't think there is a very strict convergence like that onto the calyx. So for example, if you take one Kenyan cell and look at how many projection neuron it converges to, it is roughly 50% of the population. And I don't think, I don't know for sure that that's a predetermined connection, but I think it's a difficult question to address because it's a huge number which we have to trace late and but I don't think even in Drosophila that is addressed properly.
And should one regard leukemia cells as the cortex of a mouse with possibilities for different sort of overlap?
Right.
Do you also have specific projections for the mushroom bodies to elicit different patterns of behavior, like in in a mouse when you have hypospadic projections?
So here, I think the current understanding is that the projections which go to the calyx are the ones which are required for it to animal to learn new things. So associative learning is supposed to take place in that. But those which are innate and drives behavior like carbon dioxide or repulsion in Drosophila and pheromone, like I think they are mediated to that lateral horn circuit, which so I think that's a correct notion of how it works. So that it seems to be segregated in terms of innate versus what is learned.
Okay.
Just one question about repeatability of these experiments. I mean, if time series is oscillation, suppose you have to repeat experiments, do it exactly that time, and if it's not, then how do you make some time series correlations so that you can extract the relevant information?
Yeah, so we can record from multiple cells. So we can record from 20, 30 cells at the same time. So which would some sense representative of population for hundreds of. So in that subpopulation we can look at it in the time-based correlation across the cells. But the order delivery system which we have is not time precise enough that across animals or across trials we can look at the temporal ordering at the time scale of 50 milliseconds, which is the, but it is sufficient for looking at temporal time scales of the response to the altered in the hundreds of milliseconds. So within the same animal we can look at time correlation at this kind of time scale.
But I mean, the time plot is going to be quite different again and again. Then the meaningful question is not to see whether that time series correlates with the neighboring cells or with over a sample of organisms. But once you extract some feature out of it and say, okay, this is the generic. So what would that be?
Yeah, so people don't look at, for example, the synchronization as, okay, if it is synchronized this way, it codes for something, synchronized this way, it codes for something. I don't think people look at it that way. What people think is that, or at least the current hypothesis is that synchronization helps in efficiently driving the Kenyan cells. And it narrows the window of integration over which the Kenyan cells take information. And so that in some sense saves spikes. Maybe there are mechanisms which are there for synapticking the Kenyan cells like calcium dynamics, which may require this kind of quiescent period where no input comes in for something to happen like STDP, which has been shown to take place between the synapse of the Kenyan cell and for the neuron which are the beta lobe of the. So people tend to think that notion of why synchrony is required, not about coding for something.
I have a question about your fashion walk. I was curious whether if you put the same grasshopper again and again, does it learn that that gap is
We
there?
don't know yet. We are looking.
And is the response always when it comes to the gap that it flies
Yeah,
off?
yeah, it does not.
Completely
It's not.
different motor pattern.
It is not true for all animals. Some of them may, they are restless creatures. Some of them may jump off immediately. But those who walk, they walk and then reach the end. And the walking pattern I should show is not uniform. So some of them do this alternate, some of them do this together and they switch. But nevertheless, all of them, if they are walking at a steady pace, overshoot and then come back.
At the end of the response is always a switch of motor
Switch of
pattern.
mode, yeah. So they will do a search initially, and then they will jump or may not jump.
Are there any fundamental differences in connection between the grasshopper, the structure, and the fruit fly? Or is it almost identical?
No, I think there are quite a bit of differences. For example, I think the calyx to lateral horn ratio, if you take in fruit fly, is very small calyx, large lateral horn. Grasshopper in many other systems, large calyx, small lateral horn. I tend to think that that's because of the innate behavior control is more in Drosophila compared to these other species. So if you take honeybee, which is the extreme of learning ability in insects, then you have much larger and multi-structured calyx.
So we should thank Jyoti.
Thank you.